We are looking at elementary statistics practice test number 3. Module 3, chapter 6 and 7, chapter 6, normal probability distribution, chapter 7, estimating parameters and determining sample sizes. I'm going to answer the following questions, and this is chapter 6, normal probability distributions. What percent of normally distributed data value lie within 2 standard deviations to either side of the mean? I hope everybody remembers that from the empirical rule was about 95%. So how did they come up with that? That's the idea behind that. If we look at the concept within 2 standard deviation means probability of z between -2 and 2, and they come up with a rough estimate of 95%, precisely is 95.44%. I hope you remember when we start from the mean and we go 1 standard deviation on each side, we cover about 68%, 2 standard deviations, 95%, 3 standard deviations, almost everything, 99.7%. For a continuous random variable, the probability of a single value is always 0. The reason why, because a single value does not cover any area. Remember, the area under the curve represents the probability, the total probability, which is equal to 1 on each side, 0.5. For normal distribution, the parameters are mu and sigma, the mean and standard deviation, and those values for SND, standard normal distribution. It's something we should know. Mu is 0, sigma equals to 1. We want to find the z-value for a standard normal distribution such that the area in the left tail is 0.05. It's a good practice to always graph to be on the safe side. So right away from the fact that this is symmetric and this is 0, this must be some negative value. So here's how the table works. Here's the TZ table. Inside the body is the area, and those are the z-scores. So for example, this one would be -3.6, 0, or just -3.6, whereas this one would be -3.61. That's how we read that. So with that being the case, we are looking at the area being 0.05. That doesn't exist. In the body, we look for the two numbers close. The number is in between those two values. Therefore, -1.64, -1.65, somewhere in between is the answer, and z becomes -1.645. However, you can use a technology for a simple question like that, using second variables and inverse norm, putting the area, the values of mu and sigma accordingly, and it gives you the answer, of course, with a lot more decimals. Now we want to find the z-score when the area to the right is 0.1. So with that being the case, when we do the drawing, we come up with that. We can go to the z-score of positive values. In some texts, they do have both of them. In some texts, they don't. And in some texts, they start from here on. So you want to be very careful the way you read the table. So with that being the case, the area is 0.1. And the cumulative area to the left is 0.9 in the body, which is this one now. You look for 0.9. It doesn't exist. It's between those two values. And therefore, you come up with 1.285. The other method would be if you use the -1, by symmetry, if I put the value here, I get the same value but negative, and now because we want it to be in the right tail, we negate that. Or, so we end up with -1.28, -1.29, and we negate that, we make it positive. So, of course, you can use a technology. Make sure you put the area as 1 minus 0.9, and that's extremely important to be careful of. giving us the answer again with a lot more decimals. Probability of z larger than negative 0.82. Graphing is extremely important because right away we realize each side is 0.5, so this shaded region must be larger than 0.5. Now, this shows the area to the left. Therefore, we subtract it from 1. We come up with the answer. Again, we could use the technology, but if we will use the table, we would come up with the answer accordingly. As far as technology is concerned, for TI calculator, you use the command normal CDF. You put the proper information, lower, upper, and so on. Now, this goes from the lower, whatever the number is, all the way to infinity in essence. And for calculator, all you have to do, pick a fairly large number. 1,000 is large enough, 10,000, okay? Because this goes to infinity. Remember, beyond 3 standard deviations, it goes from -3 to +3. It goes almost 100% or 99.7%. Therefore, 1,000 is a good number to choose, or anything larger than that. And you come up with the answer, again, with much more decimals than what we got from the table. The z-value for mu of normal distribution is always 0. The reason being because z is x minus mu over sigma. You're going to replace the x with mu. And what this means is if the z-score is 0, that means the score is equal to the average score, the mean. If it's positive, then the score is above the mean. And if it's negative, it's below the mean. Usually, the normal distribution is used as an approximation to binomial distribution when NP and NQ are large. How large is large? Larger than or equal to 5. In many texts, including Mom, My Open Math, must be larger than or equal to 10. We want to find the area of this shaded region. The graph gives us the standard normal distribution. That means the mean is 0, standard deviation is 1. Simply put, mu is 0, sigma is 1. And the graph clearly tells us the area to the right of negative 0.93. Looking up the table or technology, at this point, we've had enough practice. We come up with the answer. And this is table, this is technology, normal CDF. Now we are dealing with the IQ scores. The graph depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15, which means mu is 100, sigma is 15, and we want the x between 106 and 132. We have to change the x score to the z score using the formula x minus mu over sigma. So we go from normal distribution to standard normal distribution, and we either use the table or technology. We come up with the answer.
Assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. Part A, find the probability that a given score is between negative 2.13 and 3.77 and draw a sketch of the region.
Perfect. So what is given? Mu is 0, sigma is 1. When we do the drawing, we are interested in finding the probability of the z-score between the two numbers, negative 2.13 and positive 3.77. Again, at this point, you are showing all your work. Using technology would be good enough to give us the answer. Notice the lower, the upper, mu is 0, sigma is 1, and of course, more decimals involved. Now, in this case, we want to draw a graph to find P19, the 19th percentile. So the very first thing is to do the drawing, such that the area to the left is 0.19. It doesn't have to be to scale, it doesn't have to be perfect. So the idea is that we are separating the bottom 19% from the top 81%. So with that being the case, we need the area to be 0.19. If we go with the table, 0.19 doesn't exist, but 0.1922 as well as 0.1894, they give us two different z-scores. And so we pick a number that is either closer or in between. We could also use the inverse norm, and it results in the proper answer. Pay attention to the fact that it has to be negative.
3 out of 8 drinkers acquire the habit by age 20. If 300 drinkers are randomly selected using normal approximation to the binomial distribution, find the probability that exactly 100 acquire the habit by age 20.
As I've mentioned, when we deal with the very first thing is what is given. We should realize this is a proportion. 3 out of 8 is P and N is 300. So you're dealing with binomial distribution, or short BD. N is 300, P is 3 over 8, which becomes 0.375. So what do we need to do? First and foremost, let's calculate the Q, which is 1 minus P, because we are going to need that. The next thing is NP and NQ, their product must be large, because we are going to approximate this by normal distribution. We have to show those values are large enough, and as you can see, they are way larger than 10. We are in good shape. So we are interested in calculating the probability of x equals 100. Binomial distribution is a discrete distribution. Therefore, when we want to approximate it with a normal distribution, which is a continuous one, if we choose x equals 100, it becomes 0 because the probability of a single value is 0. Therefore, they use a 0.5 continually correction factor. They add and subtract 0.5. Now from BD, we go to ND, normal distribution. Now we are going to go to the SND, standard normal distribution, which means we are going to use Z equals X minus mu over sigma. That means we need mu, which is NP, and sigma, which is square root of NPQ. I hope you remember the formula, or you can look up the table. The formula sheet, mu is NP. Sigma is square root of NPQ. We use those to change the X values to the Z values. Now, therefore, for standard normal distribution, we want to find the probability that Z is between those two values, negative 1.55, negative 1.43. This is the shaded region. Looking up the table or technology, using the technology will give us the following. We're going to move on and look at normal CDF. As you can see, this number extremely close to what we got. If we go with the fourth one and round it, becomes identical. We can also go with the binomial distribution, and it's a binomial PDF because there's only one value of 100. And again, as you can see, extremely close, all of those values. So that's an excellent approximation. We're going to continue with the question, and the next part is asking at least 125 acquired the habit by age 20. So we have the information from the previous page. We're going to write this. Now, it's important to understand what this means. Discretely, we need the probability of x equals 125. So this means probability of x equals 125. And we go up all the way to the value of n. Probability of x equals n. So that's the meaning of a discretely. We are approximating it with a normal distribution. Therefore, we need to add or subtract 0.5. When it's only one value, we do both. But what happens when it's one? You have to figure out what to use. If we choose 125.5, in other words, add 0.5, the next discrete value would be 126, and we're going to miss the first number. Therefore, we subtract, we make it 124.5. One more time. Probability of x larger than this number. The first discrete value, integer, is 125. We are in good shape. If we put 125.5, the first number would be 126, and we miss that. Now, the rest is easy. You go from x to z, standard normal distribution, by using z equals x minus mu over sigma. Here's the graph. So we are interested in this area. Using table or technology, we end up with the following answer. At most, 165 acquired the habit by age 20. So that means binomial distribution tells us probability of x less than or equal to 165. And we do the same thing. We either put 165.5 or 164.5. We have to make a decision. And to do so, let's see discretely what it means. It means the probability of the first number is 165. And we're going to go all the way down to probability of 0 and add them all up. So the very first discrete or integer number is 165. If I put 164.5, the first number less than that would be 164. We're going to miss that. So take a look. We use 165.5 because the very first number less than that is 165. By the way, one may ask, what happened to the equality? If you put the equality here or not, it makes no difference because this is normal distribution. But over here, it does make a huge difference. If you don't have the equality, then actually this will change to 164.5. Now we go to the z-score, standard normal distribution. Using the graph, 6.3206 is way to the right here, somewhere here. So it covers almost everything, almost 100%. So if I were to put this number on this graph, I go way beyond the chart. That gives us almost 100%. The z-table above the number 3.5 normally gives us this number. And again, it really depends on what table you're using. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What percentage of people has an IQ score above 120? Well, what is given? Normal distribution with mu of 100 sigma 15. That's the first thing as we read this question and we translate. We want the probability of x larger than 120. We use the z-score, x minus mu over sigma. And remember, when we have the given, all you have to do, plug in an x, we use 120. We have this, we do the drawing beyond 1.33. It doesn't have to be to scale, but roughly this is the area. And look up the table or use the technology. 0.0918, since they want percentage, 9.18%. The next one is asking what is the maximum IQ score for the bottom 30%. Come up with the area first. And again, it doesn't have to be perfect. Roughly, this area is 0.3. Please understand, right in the middle, we have the mu. On each side, we have 0.5. So 0.3, we need to find the z-score. And then from the z-score, we go to the x-score. So coming up with the z-score, either using technology or table, z is x minus mu over sigma. If we do the cross product, we can solve for x. So multiply by sigma and then move the mu, we get mu plus z sigma. Mu, replace it with 100. Sigma, replace it with 15. And the z value, we just found it. Again, from table or technology. and this is what it gives us, and we rounded accordingly, whatever they ask us to do. So the maximum IQ score for the bottom 30% is 92.125. If we were to use the technology, we could do this, and it gives us the answer using the inverse.
Men have head breadths that are normally distributed with a mean of 6.0 inches and a standard deviation of 1 inch. If a man is randomly selected, find the probability that his head breadth is less than 6.2 inches.
Excellent. So the very first thing, what is given? We have a normal distribution with mu being 6 and sigma being 1. That's a given. It is extremely important we be able to write this and write it symbolically. We are interested in calculating the probability of x less than 6.2. What matters here, you're dealing with one subject. So probability of x less than 6.2, using the z-score, z is x minus mu over sigma. We plug in, we replace the x with this number 6.2. Normal distribution now, standard normal distribution, SND, either table or technology. We come up with the answer. Now, let's just do the graphing quickly. 0.2 somewhere here. So it's a little bit more than 0.5 as far as the graph is concerned. Now we are looking at the same question, but the main thing is we now have 100 subjects. The idea is that n is either 1 or more than 1. When it's more than 1, we use x bar, probability of x bar less than 6.2, which gives us the z-score using x bar minus mu of x bar over sigma of x bar. Mu of x bar is equal to mu. Sigma of x bar is sigma over square root of n. Mu of x bar is mu. Sigma of x bar is sigma over square root of n. We plug in. I hope you realize this is a complex fraction. Square root of 100 is 10. It really comes at top and makes it actually 10 times larger than this number, making it 2. Probability of x bar less than 6.2 is the same as probability of z less than 2. And here's the graph. So from here, number 2, we want this area. Gives us 0.9772. We could use technology as follows. If we go back to any of them, when it says x is less than 6.2, it really goes from negative infinity to 0.2 in essence. So you can put negative 100 or negative 1,000. This is the number the calculator has already chosen. I didn't change that. But if it's not, put any number small. Remember, within 3 standard deviations on both sides, we cover 99.7%. So if you're way to the left of that, you cover everything. Even if you choose minus 100, it will work. Do the math. Gives us the answer. Very close to this. In this case, notice I'm using exactly the same thing for sigma. I'm dividing it by square root of 100, and I'm showing the work here. We end up with a number extremely close to what we have here.
The assets in billions of dollars of the 4 wealthiest people in a particular country are 33, 29, 16, 11. Assume that samples of size n equals 2 are randomly selected with replacement from this population of 4 values. After identifying the 16 equals 2 to the 4th power of different possible samples and finding the mean of each sample, construct a table representing the sampling distribution of the sample mean. In the table, values of the sample mean that are the same have been combined.
I'm showing you how to come up with that. And this is a very small sample on purpose because it's very difficult if you have a large sample. So having said that, let's see how we put them together. Starting with the first number, number 33. You combine it with itself. Then the next number, 29. Then the next number, 16. And then the last number, 11. So take a look at the first 4. Now we calculate the mean for these two becomes 33. For these two becomes 31, so on and so forth. Each one has a possibility of 1 out of 16. Now, how do you do the next number? The next number is 29. So 29 with 33, 29 with itself, 29 with 16, 29 with 11. So take a look. 29 with 33, 29 with itself, 29 with 16, 29 with 11, and so on and so forth. I'm showing you how to come up with that. Now this has to be continued. And here's the table we want to come up with. The explanation here is as follows. If you look at this number 33, there's only 1 out of 16. But if you look at 33 and 29, which is 1 out of 16, we also need, we see 29 and 33, 1 out of 16, they do combine, giving us, I don't want to write 1 over 8 on purpose. I want to show you that it's 1 over 16 plus 1 over 16 is 2 over 16. So take a look. This one gives us only 1 outcome, 1 out of 16. However, this one gives us 2 outcomes, 2 out of 16, and this thing continues, and you write the rest of it. Now, we want to compare the mean of the population to the mean of a sampling distribution. To do that, first and foremost, mu is summation of x over n. So we basically add up the given 33, 29, 16, and 11 and divide by however many, which is 4. This is mu. What is mu of x bar? You calculate the mu of x bar using summation of x bar, p of x bar. That means you're going to multiply this one by this one by this one, all the way to the end. So the first column times the second column, and then add them up. They give us the same thing. Another way of doing that, look at the x bar, add up all the x bars. That's the same way. Add up all the x bars, and there are 16 categories, divide by 16. That gives you absolutely the same value. They are equal. So do the sample means target the value of a population mean? In general, do sample means make good estimates of population means? Why or why not? Here's the definition. The sample means target the value of a population mean. That is the mean of the sample means. The expected value of the sample mean is equal to the population mean. Mu of x bar equals mu. That's exactly what it means. This is the x bar for each pair. So mu of x bar means take the average of those x bars. Mu of x bar means take the average of those x bars. And they are identical.
The population of current statistics students has ages with mean and standard deviation. Samples of statistics students are randomly selected so that there are exactly 44 students in each sample. For each sample, the mean age is computed. What does the central limit theorem tell us about the distribution of those mean ages?
We were looking at this concept of a central limit theorem in the previous question, which means the central limit theorem, a sampling distribution of sample means, is a distribution obtained by using the means computed from random samples of a specific size taken from a population. For samples of size n larger than 30, the distribution of a sample means can be approximated reasonably well by normal distribution. The approximation becomes closer to a normal distribution as the sample size n becomes larger. And the conclusion is the distribution of sample x bar will, as the sample size increases, approach a normal distribution. The mean of a sample means is the population mean, mu of x bar equals mu from the previous page. I hope you remember that. The standard deviation of all sample means mu, sigma of x bar is sigma over square root of n. And therefore, in this example, since n is larger than 30, a sampling distribution of the mean ages can be approximated by normal distribution with mean mu of x bar equals mu and standard deviation sigma of x bar is sigma over square root of n. Since we know n is 44, we put sigma over square root of 44.
A boat capsized and sank in a lake. Based on an assumption of a mean weight of 137 pounds, the boat was rated to carry 50 passengers, so the load limit was 6,850 pounds. After the boat sank, the assumed mean weight for similar boats was changed from 137 pounds to 170 pounds. Assume that a similar boat is loaded with 50 passengers and assume that the weights of people are normally distributed with a mean of 174.1 pounds and a standard deviation of 35.1 pounds. Find the probability that the boat is overloaded because the 50 passengers have a mean weight greater than 137 pounds.
Excellent. This is statistics at work. How do we put it to work? Here's an example of that. So with that being the case, what is given? As we read the question, we are dealing with a normal distribution. N is 50. Mu is 174.1 pounds and sigma is 35.1. We are interested in calculating the probability of x bar larger than 137. We can calculate the zx bar minus mu of x bar over sigma of x bar. Mu of x bar is the same as mu, so we have this number. Sigma of x bar is this number divided by square root of n, which happened to be 50. Again, let me put that at top. We want to make sure that we have that. So mu of x bar equals mu. Sigma of x bar is sigma over square root of it. With that being the case, probability of z larger than negative 7.474, I hope you realize it's about 100%. Because again, if you start from the mean and go 3 standard deviations on each side, it covers 99.7%. You don't even have to look up the table. Negative 7.474 all the way to the infinity, that is 1 or 100%. So 100% chance that it is overloaded. Now we're going to change that, and we are going to look at the case with n being 15. So we are changing the n. Going back to this, we are repeating the same thing. The boat was later rated to carry only 15 passengers. We want to check the same question, but we are changing n from 50 to 15. So we are repeating the same thing. Normal distribution. We are just changing n from 50 to 15. Same mu, same sigma. So probability of x bar larger than now, this time 170, because things have changed from 50 to 15. We need to calculate the z-score again. Negative 0.4524. So we go from normal to standard normal. Probability of z larger than negative 0.4524. That is also huge because it's way larger than 0.5. The reason is larger than 0.5 because this is negative. You don't even have to graph it to see it by now. Do the new ratings are any better? Are they safer? Because there is a high probability of overloading. We're talking about 67.45%. Because there is a high probability of overloading, the new ratings do not appear to be safe when the boat is loaded with 15 passengers.
At an airport, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 10 minutes. All of the different possible waiting times are equally likely. Find the probability that a randomly selected passenger has a waiting time of at least 7 minutes.
Let's figure out what we're discussing, the concept of a uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. Now, properties. Density curve, the graph of any continuous probability distribution is called a density curve. And any density curve must satisfy the requirement that the total area under the curve must be what? 1, exactly 1. Because the total area under the density curve is equal to 1, there is a correspondence between area and probability. Therefore, probabilities can be found by identifying the corresponding areas in the graph using this formula for the area of a rectangle. Area is the height times the width. Therefore, the given is if the total area is 1 and the width is 10, the height must be a number multiplied by that equals to 1. So basically, whatever this is, the reciprocal of that. So one more time, the total area is 1, the width is 10, so the height must be 1 over 10. So that's the shape. We are interested in finding the probability of x larger than or equal to 7. So we can locate 7 and come up with the area. So this is the shaded region we want. So we know the height is 0.1. All we need is the width, and the width is 10 minus 7, which is 3. And their product is 0.3 or 30%.
Information regarding standardized tests used for college admittance. Scores on the SAT test are normally distributed with a mean of 984 and a standard deviation of 204. Scores on the ACT test are normally distributed with a mean of 20.7 and a standard deviation of 4.3. It is assumed that the two tests measure the same aptitude but use different scales. If a student gets an SAT score that is the 65th percentile, find the actual SAT score whole number.
There are two different testing, two different measurements, and we want to compare them. Therefore, let's write the information for each case. If you look at the first one, mu is 984, sigma is 204. This is for SAT. For the second one, mu is 20.7, sigma is 4.3. So if a student gets a SAT score that is 65 percentile, so we can do the drawing and notice this area is 0.65 or 65%. This is not to scale, but this is a rough estimate. So as you can see, the value of the z-score is to the right of 0. We have to figure out the z-score, and then we want to find the SAT score. We go to the x. So area to the left is 0.65. We have to figure out the z either from technology or table. Either way is fine. And then after we find the z, we go to SAT score by finding the x value. You can even use the technology to come up with this z score that we are interested in. So the z score is positive 0.385320. It has tons of decimals. Z equals x minus mu over sigma. If we do the cross product here, x becomes mu plus z sigma. Mu, we wrote it here. Sigma right here. What about the z? We just came up with the z again. The graph tells us what's going on, or the table, plug in. So the answer is that. Going back to the question, we want a whole number, so therefore we rounded accordingly, 1063. So a quick recap, 65 percentile, you come up with the area. From the area, you come up with the Z. From the Z, you go to the X score. What would be the equivalent ACT score for this student? That means we want the X score for here. So we are going to use the same formula, X equals mu plus Z sigma. This time we use this mu and this sigma. By the way, I hope you realize for sure it's larger than mu because this is a positive value. So using that one, plug in mu plus Z sigma. This time we are using that. 20.7 plus Z is the same Z score times sigma 4.3, we get 22.36. That means the SAT score of 1063, and we're going to round this also because we want to go with 1 decimal, corresponds to ACT score of 22.4. If a student gets an SAT of 1494, find the equivalent ACT score with 1 decimal. So from X, we need to go to Z, and then from Z, we go to X for the second group. So for the SAT score, we have the X value. We need to figure out the Z score. Z is X minus mu over sigma. Here's X, and we use this information. Why? Those are the information pertaining to SAT. So Z score becomes 2.5. And now we want to come up with the X score using this formula and using this information. X is mu 20.7 plus Z, we found it to be 2.5, times sigma of 4.3, 31.45. How many decimals? We need 1. So the answer is 31.5.